Hi, I'm covering section 13.3 today about conditional probability and intersection of events. So first we're going to go over conditional probability. And we're going to read the following situation. Okay, so yeah, I'm having issues with the book, so I'm trying to open the book to go to the right page. Okay, so let's share the screen. Okay, so now we know how to compute the probability of complements and unions of events. We will now show you how to find the probability of intersections of events. But first, we need to understand how the occurrence of one event can affect the probability of another event. Suppose that you and your friend Marcus cannot agree which movie to rent, and you decide to settle the matter by rolling a pair of dice. You will each pick a number and then roll the dice. The person whose number comes up first as the total on the dice gets to pick the movie. With your knowledge of probability, you know that the number you should pick is 7 because it has the highest probability of appearing. So there are 36 ways to roll 2 dice, and there are 6 ways to roll a 7. To illustrate the idea of conditional probability, let's now change the situation slightly. Assume that your friend Janelle will roll the dice before you and Marcus pick your numbers. You are not allowed to see the dice, but Janelle will tell you something about the dice, and then you will choose your number before looking at the dice. Suppose Janelle tells you that the total showing is an even number. Would you still choose a 7? And of course you wouldn't, because 7 is an odd number. Once you know the condition that the total is 7, you now know that the probability of having a 7 is 0. A good way to think of this is that once you know that the total is even, you must exclude all pairs from the sample space, such as 1, 4, 5, 6, and 4, 3 that give odd totals. Okay, so I'm going to copy this definition of conditional probability. Okay, so the notation. Okay, when we compute a probability of an event, F, assuming that the event E has already occurred, we call this the conditional probability of F given E. We denote this as the probability of F given E. So that reads as the probability of F given E, or probability of F given that E has occurred. Okay, so in that example with Janelle, you know that the probability of 7, you know that the probability of 7, given that the total is even, is 0. You have it in this paragraph. So we're going to go now over example 1. Okay, assume that you roll 2 dice and the total showing is greater than 9. What is the probability that the total is odd? So we have 2 events. Event E is the event that the total is greater than 9. And event F is that the total is odd. So we want to find the probability that the total is odd, given that the total is greater than 9. So that's what we want to find. Now, there's a formula for that. So I'm going to copy this formula. That's the rule for computing the probability of F given E when the outcome when events are equally likely, or when the sample space has equally likely outcomes. Okay. So if E and F are events in a sample space with equally likely outcomes, then the probability of F given E is the number of outcomes in both E and F over the total number of outcomes in E. So let's start with event E. Okay, in how many, how can you roll a 9? Or how can you roll a number greater than 9? That is 10, 11, or 12. You can do it in the following ways. There are 3 ways to roll a 10. 2 ways to roll 11. And 1 way to roll a 12. And ENF, that is the number of ways that the total is greater than 9 and an odd number. There's only one number greater than 9 when you roll 2 dice. That is odd. And in this case, it's 11. So now we can compute the conditional probability. The probability of F given E is the number of times that E and F occur over the number of times E occurs. So that is 2/6 or 1/3. So that's the probability to roll an even number or to roll an odd number given that the total is greater than 9. Okay, next example. This is an example that involves tables about voting preferences on page 699. Okay, so we're going to use this table for the following 2 questions. The Political Action Club has surveyed 240 students on your campus regarding the relationship between their political affiliation and their preference in the 2020 presidential election. The results are given in the following table. They organize the information in who preferred Biden, who preferred Trump, who was Democrat, Independent, or Republican. So let's suppose that a student is selected at random. So number 45. If a student is selected randomly from the surveyed, find the probability that the student is a Democrat, given that the student preferred Trump. So we're going to call the events D, Democrat, and event T, that the student preferred Trump. And they are asking us to find the probability that the student is a Democrat, given that the student preferred Trump. Conditional probability formula, that's going to be the number of times that D and T occur over the number of times that T occurs. So observe that 15 people are Democrat and prefer Trump, and 98 people prefer Trump. So that is going to be 15 over 98. And I'm just going to leave it as a fraction. And number 46. If a student is selected randomly from the survey, find the probability that the student prefers Biden, given that the student is an independent. Okay, so let's give the names again. B stands for Biden, and I for independent. And we want to find the probability that the student prefers Biden, given that the student is independent. That's going to be the number of people who prefer Biden and are independent over the number of voters that are independent. So let's look back at this table. There are 25 people who prefer Biden and are independent. So these 25 people prefer Biden and are independent, and 40 people are independent. So that's going to be 25 over 40. Or we can simplify the fraction. 25 and 40 are divisible by 5, so that's going to be 5 over 8. Okay, so you can generalize the rule of conditional probability to any probability, not just for equally likely outcomes. I'm copying that. And you can see this in terms of probabilities only. So if E and F are events in a sample space, then the probability of F given E is the probability of E and F over the probability of E. And this formula has a consequence. Okay, so the above formula has a consequence. It allows you to find the probability of the intersection of two events. Because we see now that the probability of E given F over the probability of E is the probability of F given E. So solving for the intersection, the probability of E given F is the probability of E times the probability of F given E. So this is the formula for the probability of the intersection of two events. Okay, so we're going to do examples with this formula. So back to page 698. We're going to use the following. So I'm going to keep the formula, but we're going to use this earn. So assume that you're drawing two balls with a replacement from this earn. We're doing number 23 and 24. Observe that you have 23, not 23. You have 20 balls, so 10 are green. If you count them, you will see that 10 are green, 6 are blue, and 4 are red. Okay, question 23. What is the probability that you draw 2 red balls? Okay, so the probability that you draw 2 red balls. So we're going to call E the event that the first ball is red, and F the event that the second ball is red. And we want to find the probability that the first is red and the second one is red. According to the formula, this is equal to the probability that the first ball is red, and let's show the formula, times the probability that the second ball is red, given that the first ball is red. So the probability that the first ball is red is 4/20. There are 20 balls, 4 of those are red. And the probability that the second ball is red, given that the first one is red. So if you know that the first one was red, you have 3 red balls left. So by the way, without replacement means that once you select one, you don't put it back. So if there are 20, you select one, there are 19 left. So you selected 1 red ball. If the first one was red, there are 3 red balls remaining out of a total of 19 balls remaining. Okay, so we can simplify this fraction 4/20 as 1/5. And 1 times 3 is 3. 5 times 19 is 95. So that's the probability that that you will draw 2 red balls. And number 24. What is the probability that you will draw a green ball followed by a blue ball? So let's give the names again. Event E is that the first is green. And event F, the second one is blue. So the probability that the first is green and the second one is blue is going to be the probability that the first is green times the probability that the second one is blue, given that the first one is green. The probability that the first ball is green, there are 10 green balls left. There are 10 green balls. Initially, there are 10 green balls out of 20. And if the first one was green, there are still 6 blue balls left out of 19. So there are 19 balls remaining, but still there are 6 blue balls remaining. So we can reduce this fraction that 10/20 simplifies as 1/2. And then 6/2, that's 3/19. So that's 3/1. So the probability will be 3/19. That is the probability that the first ball is green and the second one is blue is 3/19. 19. And for this matter, we can extend the technique to more than 2 events. So we're going to do an example of that on page number 27. Now, I mean, on page 698, but number 27, example 27. Suppose we draw 3 cards without replacement from a standard 52 card deck. Find the probability of drawing exactly 2 hearts. So we're going to give names to the events. The first event is that the first card is a heart. Event F is that the second card is a heart. And event G is that the third card is a heart. So the probability of drawing exactly 2 hearts is going to be, you have three scenarios. That the first and the second one are hearts, and the third one is not. Second case scenario is that the first one and the third one are hearts, but the second one is not. And actually, I can do it like this. That the first and second are hearts, but the second one is not a heart. So the complement is to indicate that the third one is not a heart. Plus the probability that the first is a heart, the second one is not a heart, so that's going to be F complement, and the third one is a heart. Or plus the probability, third case scenario, the first one is not a heart, but the last 2 are hearts. So I'm going to do this once. I'm going to find each probability separately. Let's start by finding, by the way, a standard deck has 52 cards. And out of those 52 cards, 13 are hearts. So let's start by finding the probability that the first is a heart, the second is a heart, but the third one is not a heart. That is going to be the probability that the first card is a heart times the probability that the second card is a heart, given that the first one is a heart, times the probability that the third card is not a heart, given that the first 2 are hearts. The probability that the first card is a heart is going to be 13. It's going to be 13 over 52. The probability that the second card is a heart, given that the first one is a heart. So if the first one is a heart, and you are drawing cards without replacement, there are 12 hearts left and 51 cards left. And the probability that the first one is not a heart, given that the first 2 are hearts, there are 50 cards left and 39 cards that are not hearts left. So we can simplify this fraction. 13 over 52 is 1/4. Then 12 over 51. This is, they are divisible by 3. So this is 4 over 17. And 39 over 50, I don't see how I can simplify that. Oh, yes, I can. Yes, I can still do something like 4 and 50. I can simplify that as 2 and 25. 2 and 25. And anything else? Oh, there's something else. Also that 2 and that 4. So that's 2. Okay, so what do we have? We have 39. And then 2 times 17 is 34. 34 times 25 is going to be 850. And that's a 39. Okay. So we have one. The probability that the first card is a heart, the second one is not a heart, and the third one is a heart is going to be the probability that the first card is a heart times the probability that the second card is not a heart, given that the first one is a heart, times the probability that the third card is a heart, given that the first is a heart and the second one is not a heart. The probability that the first card is a heart is 13 over 52. The probability that the second card is not a heart, given that the first one is a heart, there are 39 hearts left and 51 cards left. And then the third card, if one was a heart but the other one wasn't, there are 12 cards. There are 12 hearts left out of 50 hearts. So compared to the first case scenario, and there are the numerators are the same, but they are in different places. So that fraction is still going to simplify as 39 over 850. And the third case scenario is the probability that the first one is not a heart, but the second and third are. So that's the probability that the first one is not a heart, that the second is a heart, given that the first one is not a heart, times the probability that the third one is a heart, given that the first is not a heart, but the second one is a heart. The probability that the first one is not a heart is 39 over 59 over 52. So there are 39 cards that are not hearts. And that's by the way a complement. The probability that the second one is a heart, given that the first one is not a heart. So if the first one was not a heart, there are 13 hearts left and 51 cards left. And the probability that the third one is a heart, given that the first is a heart, but the second one is not, there are 12 hearts left and 50 cards left. So same numerators, they are just in different places. This is also 39 over 850. Okay, so the probability of drawing exactly two hearts, we're going to add 39 over 850 3 times. So thus, the probability of drawing exactly two hearts is going to be 39 over 850 plus 39 over 850 plus 39 over 850. 39 plus 39 plus 39 is 117 over 850. And we saw that 850, it's 850 is 2 times 17 times 5 times 5. But none of those factors divide 117. 117 is 3 times 3 times 13. So yeah, they don't have any factors in common. Okay, the next part is probability trees. Next topic. So recall that the three-way principle in section 1.1 tells you that drawing a diagram is a good problem-solving technique. You will find that it's often very helpful to draw a probability tree to help you understand a conditional probability problem. Okay, so I can copy this definition, but the best way to illustrate this is with an example. Okay, so we can represent an experiment that happens in stages with a tree whose branches represent the outcomes of the experiment. We calculate the probability of an outcome by multiplying the probabilities found along the branch representing that outcome. And we will call these trees probability trees. So if this doesn't tell you anything, I'm going to show you this example to make it clearer. Okay, so I'm going to copy the following probability tree on page 698. Okay, so this on page 698, and I'll tell you what this means. Okay, the editors of AutoWeb have evaluated several European and Japanese crossovers and given them either a high or an average safety rating. The probability tree summarizes the results of the study. So this is how the probability tree works. Note that you have E and then H. So the probability of E is 0.4 and the probability of J is 0.6. So the probability that the car is European is 0.4 and the probability that the car is Japanese is 0.6. And the second branches, that's going to be, you have H and E. The probability that the car has a high safety rating given that the car is European is 0.65. The probability that the car has an average safety rating given that the car is European is 0.35. The probability that the car has a high safety rating given that the car is Japanese is 0.75. And the probability that the car has an average safety rating given that the car is Japanese is 0.25. Okay, so let's do number 32. Or maybe I don't even need to copy that. I can just write it. So if a car from the study is selected randomly, find the probabilities indicated in exercises 32 to 34. So on 32, they ask you for the probability that the probability of H given E. The probability that the car has a high safety rating given that the car is European, and you can see it from the tree. From the tree, you can see that the probability is 0.65. And number 33, find the probability that the car is European and has an average safety rating. So we know this formula for the intersection of two events using conditional probability. The way this is set up, we first need to find the probability that the car is European and multiply by the probability that the car has an average safety rating given that the car is European. the probability that the car is European is 0.4. And the probability that the car has an average safety rating, given that the car is European, is 0.35. The product of this probability is 0.14. Okay, and the last part is dependent and independent events. So that has to do with conditional probability. Two events are going to be dependent if the outcome of one event is affected, the outcome of an event is affected by the occurrence of another event. So that has to do with conditional probability. So let me copy that definition. That's on page 696. Events E and F are independent events if the probability of F given E is equal to the probability of F. That is, the fact that E occurred does not affect the probability of F. If the probability of F given E does not equal the probability of F, then the occurrence of E is affecting the probability of F, and it is said that the events are dependent. So last two examples, you are going to determine whether the events are independent or dependent. So these are on page 698. We're doing number 35. Okay, so in exercises 35 through 40, an experiment of two events and an experiment and two events are given. Determine if the events are independent or dependent. So the experiment is that a penny and nickel are flipped, and the events are head on the penny and tail on the nickel. So let's give them names. Event E, we're going to call this head on the penny. And F, tail on the nickel. So looks like these are going to be independent. The outcome of one coin should not be affected by the outcome of the other one. But let's verify with probabilities. And let's say we are going to find the probability of F given E. But you can also try the probability of F given E given F. That's not the number of elements in E and F over the number of elements in E. Okay, so the sample space. Okay, the sample space is what? Is head, 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 tail, tail, head, and tail, tail. So the number of elements in ENF is what? Is 1. There is only one way to obtain a head on the penny and a tail on the nickel. So it's either both heads or head on the nickel, tail on the penny, or head on the penny, tail on the nickel, or both tails. And there are two ways to obtain a head on the penny: head, head, or head, tail. So the probability of F given E is going to be 1/2 or 0.5. And the probability of tail on the nickel is also 1/2. So also, and I should have started with that because that part is a lot easier. So also, the probability of tail on the nickel is 1/2. Thus, the probabilities are the same. The probability of F given E equals the probability of F. So the events are independent. And number 38, that's going to be the last one. What dependent events look like? Okay, so 2 balls are selected randomly without replacement from the urn shown in exercise 23. The outcomes are the first ball is red and the second ball is green. So I'm going to copy the urn that we work with. Okay, so we have these events. I'm going to give the names. I'm going to call the first ball is red. I'm going to call it this E. And the second ball is green. I'm going to call it F. So we need to compare the probability that the second one is green, given that the first one is red, and the probability that the second ball is green. Okay, so let's start by finding the conditional probability. The probability that the second ball is green, given that the first one is red. So if the first one is red, there are 10 green balls left and 19 balls left. That was easy. We need to compare this to the probability that the second ball is green. Now that one, okay, so the second ball is green. Well, we don't know whether the first one was green or not. So we can do this, how we can split it. The probability that the second ball is green, that's going to be the probability that first is green and second one is green, plus the probability that the first is not green and the second one is green. So the probability that the first is green, that the second one is not green. So conditional probability, remember, conditional probability says this, that the probability of, I'm going to use other letters, G and H, is the probability of H times, or the probability of G for this matter. I mean, the order is not that important, times the probability of H given G. Okay, so we have 2 case scenarios. That's going to be the probability that the first ball is green. The probability that the first ball is green is 10/20 times the probability that the second ball is green, given that the first was green. So that's, if the first one was green, there are 9 green balls left and 19 balls left. Plus the probability that the first one is not green, which is also 10/20. times the probability that the second ball is green, given that the first one is not green. So there are 10 green balls and 19 balls left. Okay, so that's what. This is 1/2. And I'm just going to keep, for now, I'm going to keep the same denominators. So that's 9/38 plus 10/38. 2 times 19 is 38, so that's 19/38, or 1/2. So finally, okay, let's compare the probabilities. This was the probability of F given E, and that was the probability of F. So you can see clearly that the probability of F given E does not equal the probability of F. So you're selecting items without replacement. That means the second event is going to be affected by the outcome of the first. So conclusion is that the events are dependent. Okay, thank you for listening.